Ah, logarithms, the black sheep of the function family. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking a look at some of the slowest functions in the basic function families, logarithmic functions. Logarithmic functions are the first of our inverse functions. So if you need a primer on inverse functions, you can check out the link here. But the thing to remember is that logarithmic functions are the inverse of exponential functions. First of all, the thing to remember about inverses is that they undo each other. So if I take f of inverse f of x, I get x on the other side. Graphically, this means that inverse functions are reflections of each other across the line y is equal to x. So if logarithms are the inverses of exponentials, then I can just take the graph of the exponential function and flip it across the line y is equal to x, and I get this graph, which is a logarithmic function. So now that we know what it looks like in general, let's investigate some of its properties. First of all, what are logarithms? Well, logarithms give the exponent for a relationship such that the base raised to that exponent gives the argument of the log. So if I have the expression 2 cubed is equal to 8, I can rewrite that expression as the log base 2 of 8 is equal to 3. 3 is my exponent in the exponential formulation here, and it is the value of the logarithm. 8 is the value of the exponential and the argument of the logarithm. 2 is the base in both of these formulations. Another way of thinking about logarithms is to ask the question, to what number must I raise the base of the logarithm to get the number in the parentheses? We can begin to see how the shape of these functions forms. So the parent function for logarithms is f of x is equal to the log base b of x. All logarithms have a base b, and their argument is the input, x. In standard form, logarithms look like this. F of x is equal to log base b of x minus h plus k. Like usual, h conforms to our horizontal shift of the function, left or right, and k conforms to the vertical shift of the function, up and down. b is going to be our base, but it also, like with exponential functions, it represents a stretch or squish, a scaling of the function. Notice, like with exponential functions, I could write this function like this: a times log base b of cx plus h plus k. But those two other constants, a and c, are redundant in this case. I can do the same thing by manipulating a as I can when I manipulate b, and I can do the same thing with c by manipulating k and b. So let's talk about what our base b must be. Like with exponential functions, b must be greater than 0. It also has a stipulation here that it cannot equal 1. So remember, with exponential functions, if b is equal to 1, then we get that horizontal line. Well, because logarithms are the inverse of exponential functions, when b is equal to 1, we would get a vertical line, which has an undefined value as a function. So we can't have b is equal to 1 for a logarithm. There are more complex explanations for why this is, but we can't have the log base 1 of x. The end behavior of the function is determined by this number b. So if b is greater than 1, then the function increases from negative infinity to positive infinity. And if b is between 0 and 1, then the function decreases from positive infinity to negative infinity. Notice that for all logarithmic functions, we have a vertical asymptote, much like we have a horizontal asymptote for all exponential functions. For the base logarithmic function, log base b of x, that vertical asymptote is always the line x is equal to 0, or the y-axis. But for a general logarithmic function, that vertical asymptote is equivalent to the line x is equal to h. Note that by changing b to its reciprocal, so if b is equal to 2, changing that to 1/2, that indicates a vertical reflection of the function. This is actually the same thing that happens when we multiply the whole function by -1. Now, what about that other side of the vertical asymptote? Well, it's important to note that the logarithmic function, the argument of the logarithmic function, can never be negative. So x minus h can never be negative. So for instance, we saw with the parent exponential function b to the x power that it has a horizontal asymptote at y is equal to 0, and therefore its range is from 0, non-inclusive, to positive infinity. Now let's take a look at the logarithmic function, which is its inverse. So the domain now of the logarithmic function must be the range of the exponential function, which again is from 0, non-inclusive, to positive infinity. We can plug in negative values of x if h is positive. So if h is 2, I can plug in values of -1 for x and still get a valid solution for this logarithmic function. So we've talked about the domain, but what about the range? Well, the range of this function is just the domain of an exponential function, which is from -infinity to positive infinity, all real numbers. But just as an exponential function gets to positive infinity very, very quickly, a logarithmic function gets to positive infinity very, very slowly. So if I look at the base 10 logarithm, so let's say, what's the log base 10 of 100? Well, the y value of that is just 2. And if I plug in the value of what's the logarithm base 10 of 1 million, I get a y value of 6. If I plug in a value of 1 billion for x, I get a y value of 9. So for big jumps in x, I get very small jumps in y. Finally, let's take a look at our x-intercepts for a logarithmic function. These are analogous to our initial value for our exponential functions, or our y-intercept for our exponential functions. So just remember that for exponential functions, when I raised something to the 0th power, I got 1 on the other side for our parent exponential function. For our parent logarithmic function, we will get the function equal to 0 when the argument of the log is equal to 1. So for a simple logarithmic function, so log base 2 of x, my x-intercept will always be 1. This is complicated when I add in an h or a k term, because the function will then be shifted left or right or up or down, but we can simply solve the logarithm by setting that entire function equal to 0 and solving for x. That will give us our x-intercept. In general, the x-intercept is equal to b to the -k power plus h. In a future video, we'll go over what logarithms really are and what they do and the properties of logarithms. But for now, let's try out a problem involving logarithmic functions. Find the intersection point or points of these two logarithmic functions. F of x is equal to log base 2 of x minus 1, and g of x is equal to log base 4 of x plus 11. Try it out yourself, and I'll see you in the solution.